For this practice, we have a 1018 steel, and then we prepare a 400 milliliters copper sulfate solution, and we introduce the steel into the solution. After that, we took it out and we started drying it with hot air. Then we insert the piece into the oven at temperature above 727 Celsius degrees. Then we took it out and we move it into the JOMINY device in order to cool it at a certain cooling rate. Then we remove 4 millimeters from the piece and we took it to the Rockwell. We make a Rockwell C harness test, and finally we graph the results we got, and we have the JOMINY curve. Steel is an allotropic material, and if it's in the crystallographic structure BCC, it is the way that this steel can be harder than any other. Also, it is important to mention that there is a big difference between all phases that we are going to analyze in this practice. That is lignite, martensite, pearlite, and austenite. And specifically, martensite is the best one because there is a fast change from austenite to martensite. So there is no time for carbon to change its original composition, and there is no opportunity for diffusion.
The ASTM standard JOMINY we found is the A255. This is for the steel mills. The function of this is to find the hardenability of our steel and how efficiently is our steel, making a series of proofs to determine from where the proof is hard to getting low to the center. About the calculation, we got that our steel it have 7 grain number of grains, so we got this percentage to get the ideal diameter for only the JOMINY the ideal diameter.
Hardenability is a property of metals and steels to determine how easy is to be for a steel to be quenched and for martensite. Temper it's a term often used to indicate the cooling time, and also is a measure of how long a steel can spend heated in water after a quench. Now the real diameter, it's the diameter that every material can has of martensite, but it has variations. For example, 1018 will have less. It must have a less diameter than 1045. The ideal diameter it's a quantitative measure of steel's hardenability, and it refers to the largest diameter of a steel that can be quenched to produce at least 50% martensite of its center. Now I'm going to explain the correct tempo. That is, cooling down. It's when you cool down the piece in the shortest period of time, and letting the piece to have a good tempo and don't have any relation with ambient temperature.
The ideal diameter is the diameter that we wanted for quench the 50% of the steel to convert martensite. We got in our proof that the better ideal diameter of the steel 1018 it has to be 3.6 millimeters, or also that will be in inches have to be 0.1520. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20. 20.
Now we're going to calculate the cooling rate at 25 millimeters in the test tube that is going to be in this point. As we have 25 millimeters, we need to transform this unit to inches, and we have that is 0.9842 inches. And then we can know that the cooling rate is going to be approx 5 Celsius degrees per second.
As we can see in this figure, the critical cooling rate is decreasing while the outstanding grain size is increasing. With this, we can say that the hardenability is increasing. The relation between the critical cooling rate and the outstanding grain size can be obtained with this formula. This R means the critical cooling rate, that is in Fahrenheit per second. This capital N means the outstanding grain size per inch square at 100 diameter. And this N is a constant that is generally 0.4, and this K is another constant that depends on the material. Outstanding grain size of any steel is included by four things. First one, the initial grain size. Second one, the mechanical deformation that is made in the hot or cold work, the rate of heating to the outstanding condition, and the time and temperature of heating.
Now we're going to analyze how the JOMINY device works. You take out the sample fast from the oven and put it in the JOMINY device. Then water starts going up, touching the edge of the sample, cooling it. So you start, if you pass from austenite from martensite fastly, so the bottom of the piece is going to be harder than the top because of the cooling. Out of the oven and we put it into the JOMINY device. There we can analyze all the faces that our piece had. At the bottom we have the martensite, then the vinite, then the pearlite, and at the top the austenite face. Also we can note with this that the bottom of the part, that after doing the rock wall, that is the hard part of the test tube.
From our hardness graphic, we can see that the hardness part of our piece is at the lower end, that is of the martensite face. And where we are getting farther from this part, the hardness is decreasing because we have another faces in our piece. From our graphic, we can also see that in the martensite part, the average of the hardness is more or less in the range of 25 to 30, and the theoretical tell us that it's almost in the same range. From this practice, we prove that each of the phases have different mechanical properties, and in our laboratory we note each of them. We also note that we have to be above the A1 curve so we can obtain the austenite, and once we have the austenite, then we can achieve any other phase that we want.
For me, this practice was very useful because we used the carbon diagram and the TTT diagram. We were able to check all the phases in our test tube. Well, only the austenite, the pearlite, the vinite, and the martensite. And it was very interesting designing all the process in order to make the material more hard in the edge than in the center. So now we can make an application to this.
In conclusion, in this practice I got very important information about the JOMINY process, to how important is it for creating the martensite and how the temperature involves all these factors to show us the different phase about a steel and how we can manipulate the steels to becomes better and have better properties on that.
For me, this practice was very interesting and very important for a mechanical engineer like us because we can have like an empirical reference of all of these experiments, and in the future, if we are experimenting with some metals and we need those metals to be harder and to have better mechanical properties, we can have like, as I said, an empirical reference of this experience.
So, from this practice, I learned the different type of phases that we can have in some pieces, and I also identify each of them and what characteristics and properties are in each of them. This can help us as engineers to make any material depending on the characteristics that we need.